Hey everyone, I am Jain. Last time in part 1 of our SVM series, we covered what SVMs are and how to formulate the problem. In this video, today, we will understand the method of Lagrangian multipliers and the KKT conditions to solve the optimization problem. Watch the video till the very end because to stand out as a data scientist or a ML scientist, you have to understand the mathematics behind every algorithm, not only the SVM. I'm going to upload videos soon on every algorithm, but as of now, watch this video. And this video is important for the next part, which is part 3. That is the reason you have to watch the video till the very end. Let's dive in. Guys, in the last video, we came up with this goal. We want to find the value of W and D to maximize the f of W. What is f of W? 2 by norm of W. It is becoming an optimization problem. We want the optimum values of W and D subjected to a constraint y into W dot xi plus D greater than or equal to 1. If you not watched the previous video, please go and watch it, then come to this video. You will understand better. Now, Lagrange, how Lagrange will help us? Let's see, guys, in this video. The Lagrange multipliers. Joseph Louis Lagrange invented a strategy for finding the local maxima and minima of a function subjected to equality constraint. Equality constraint, guys, subjected to equality constraint. Let's see what is the method of Lagrange multipliers. Lagrange noticed that when we try to solve optimization problem of the form minimization of f of x subjected to g of x equal to 0 equality constraint, the minimum of f is found when its gradient point in the same direction as the gradient of g. Gradient of f point in the same direction as the gradient of g. In other words, gradient of f is equal to alpha times the gradient of g of x, right? See, let's suppose gradient of f is going in this way, and gradient of g of x is also going in this way. Means there should be a linear multiple. A scalar should be there, right? That's what he said. And so if we want to find the minimum of f, if you want to find the minimum value of f under a constraint g, we just need to solve for this equation. This equation, gradient of f of x minus alpha into gradient of g of x, where alpha is the Lagrange multiplier. To simplify this method, now what does it mean, gradient of f of x? To simplify this method, see, this is our Lagrange function del f of del lam L of x comma alpha. The follow we have to follow these three steps, guys, to apply this method. First step is to construct the Lagrange function and introduce one multiplier per constraint. One multiplier per constraint, guys. Remember this. It's a very important point. The second is to find the gradient of the Lagrangian. But in our previous video of the math behind PCA, we solve the Lagrange function as taking the partial derivative. Partial derivative of one variable, partial derivative of L with respect to one variable, we will be equating to 0, and another variable we will be equating to 0. But here the gradient is there. Both are same, guys. Applying gradient and equating to 0 is same as applying the partial differentiation with respect to each variable. That is all we are doing. Instead of x, we will here dou by dou w will be there. Instead of y, here there will be dou by dou d for our problem. For our problem, it is homework for you. How the gradient will be equal to applying gradient on L will be equal to doing the partial differentiation with respect to each variable. Try to do this. Now let's apply the SVM Lagrangian problem. Recall, what is our goal? To maximize the f of w. So we know a method to minimize a function. We will do the reciprocal of it and we will do minimization, right? We have a method, guys. Why won't we use this? To use this, we have to minimize the function. Okay, maximizing f of w is same as minimizing the 1 by f of w, right? The reciprocal. That is what I have done. Now our new goal is to minimize this w square, norm of w square by 2, subjected to yi, subjected to this constant yi into w dot xi plus d minus 1 greater than equal to 0. Now you will question, why squaring? Because squaring is nothing but squaring will give the advantage of removing the square root. Removing the square root for the inner product. See, norm is defined as norm square is equals to inner product. Now here inner product is dot product. Now we will be removing the square root, right, for the dot product. That is the reason we will square this. Now the Lagrangian problem is, this is our new f of w, and this is our gi of w, our constraint, and I am defining the Lagrangian function f of w minus summation alpha a into this. Substituting the values, we came up with this Lagrangian function. We introduced the Lagrange multiplier for each constant. We don't have one alpha, guys. We have m alphas, because we have I data points and I labels for them. So we have to introduce the Lagrange multiplier for each data point, for each label, nothing but. I hope you understood. That is the reason we wrote here summation I equal to 1 to m, where we want to find the Lagrange multiplier for each data point. And the important part is, we know that the Lagrange method is applicable for the equality constraints, but we had a inequality constraint. We had a inequality constraint. Why we are using Lagrangian function? Is it still valid? Yes, guys. Yes. But the Lagrangian function, on solving the Lagrangian function, the values of w and d may not be optimal. This is what KKT says. KKT says, Karsh Kantakar says, hey Lagrangian, the values on solving your problem will not be optimal, since you are using the inequality constraint. So if the values that you get of w and d, if they satisfy my conditions, definitely those are optimal. This is what KKT says to Lagrangian. Okay, okay. Now let's see what are the KKT conditions with an example. With this, see, f of x1 comma x2, this one, and we have two constraints here, two constraints h1 and h2, two inequality constraints with minimization problem f of x1 comma x2. KKT says first we have to do the partial differentiation of L, the Lagrangian function, and you have to equate to 0. And the second is to multiply the Lagrange multiplier and the constraint and equate to 0, which means lambda 1 into first constant equal to 0, lambda 2 into second constant equal to, like that. And the third one, every constant should be less than or equal to 0. And the fourth one is every Lagrange multiplier should be greater than or equal to 0. These are the four conditions of KKT. Now let's apply each condition for the example, for this example. And I wrote Lagrangian function f of w minus lambda 1 into the first constant minus lambda 2 into second constant. And after doing the partial differentiation with respect to all the variables, I got two equations, 1a 1b and x3 equal to 0. And second condition, multiplying the Lagrange multiplier with the constant and equating to 0. And same, I named them as 2a and 2b. And the third condition, making the inequality less than or equal to 0. I have done those. And the fourth condition, every Lagrange multiplier should be greater than or equal to 0. And let's take case 1. Let's suppose both lambda 1 equal to 0 and lambda 2 equal to 0, or Lagrange multipliers are equal to 0. And on solving, we will get x1 and equal to 2, x2 equal, because we have 1a and 1b. We have two equations, right? So you keep lambda 1 equal to 0, lambda 2 equal to 0, you will get two equations, and solve for x1 and x2. You will get x1 and x2. And let's check whether this x1 and x2 satisfying the condition 3 or not. No, they are not satisfying. You can see them clearly, right? Pause the video and see it. because unnecessary the video length will become long, right? Pause the video and see them. And now let's go to the case 2. Case 2. See, lambda 1 is not equal to 0 and lambda 2 is also not equal to 0. Let's take them. And the 2a, let's take the 2a right now. Let's take this 2a. What is the 2a? Multiplying the Lagrange multiplier with the constraint and equating to 0. Now, one of them is not equal to 0. We know that lambda 1 is not equal to 0. And x1 plus x2 minus 2 is equal to 0. What does it mean? It means that the x1 plus x2 minus 2 equal to 0, right? Means we got one equation now. And similarly, from 2b, another equation will be coming. See, from 2b, we'll get another equation, another equation, another equation, and solving these two equations we will get x2 and x3, and we got x1 and x2, right? Substitute them in 1a and 1b, you get lambda 2 equal to minus 20. Oh, but lambda should be greater than or equal to 0. The fourth condition says, means case 3. Case 2 is also failed. Let's go to case 3. Case 3 says, let's take lambda 1 equal to 0 and lambda 2 is not equal to 0. And substitute 1a in 1b and we will get solve this, guys. I think it's basic mathematics. Do them. And we are not satisfied this condition as well. See, the case 3 is also failed because we are on keeping the values x1 equal to and x2 equal to 3 in 3 and 3b, we are getting this 3 is less than or equal to 0. How 3 will be less than or equal to 0? No, right? Means this is also failed. Now the case 4, lambda 1 not equal to 0, lambda 2 is not equal to 0. On solving, we get lambda 1 equal to 3. Solve this, guys. This is homework for you. Lambda 1 equal to 3, x1 and x2. We got this. And on substituting the x1, x2 in 3 and 3b, see, conditions are satisfied. Means we got the optimum values. Now let's apply. We understood the KKT conditions with the example, right? Now let's apply with the S on the SVM. This is our Lagrangian function. This is our Lagrangian. And first, what we have to do? We have to do the partial differentiation with respect to the w and equal to 0. And I hope you know how to do the partial differentiation. See, the w norm of w square will be 2 times w, and I have done that, and I taken dou by dou w inside. This will be x, this will become xi, and it will become 0, the third term. I hope you can see my cursor. See, this will become 0 because w is term is not there. Remain all the other variables will be constant, and so because of that, differentiation of a constant will be 0, right? Similarly, like this. And we came up with the w. We came up with the w as this summation of alpha 1 equal to 1 equal I equal to 1 to m alpha a y a x a. Now let's solve for d as well. Similarly, on doing the partial differentiation, I hope you know how to do the partial differentiation, and we came up with this result. Now let's carefully substitute this w in the Lagrangian function. See, I am writing w square as w dot w because w dot w dot product of w dot w is equals to w square, right? That's the reason I have written like this. And w is equals to, we came up with this one, I equal summation I equal to 1 to m alpha I y I x I, and I wrote this same as that. And here I wrote j equal to 1 to m alpha j y j x j. Why I wrote like this? Because we should not have to, on writing that we have to get some understanding, right? After writing like this, what I am getting, the understanding that I got was, we are taking the dot product of each and every data point with other data point. Let's say there are m data points in your data set. You are taking the first data point and doing the dot product with every other data point. That's what we're getting the intuition here on writing j equal to 1 to m. I hope you understood. And minus, and I wrote the w with w here because I have to, here also w is there, right? Here also w is there. I have to substitute w value here also. See, I substituted wj equal to 1 to m dot xi plus d, or our constraint, and I took the summations outside because, and then the summation, they are scalars, right? And alpha I y are scalars, alpha I alpha j are scalars, and yi yj also, because yi is nothing but negative label or positive label, -1 or +1. Those are also constant. Those are also constant. Now xi and xj are the vectors. The dot product will be between these two. And similarly, taking the summation inside the alpha I inside, multiplying the alpha and summation inside alpha I alpha j, yi yj, and x dot xi dot xj. Similarly, we got this, and multiplying this summation of alpha I yi to with this d, we get this, we get this, and multiplying alpha we get this. I hope you understood this calculation part. It is very important to understand. If you haven't understood, please mention in the comment section. I will try to clarify your doubt. Now, see, this will be 0. Why? Because we came up with this equation, right? With this equation. And finally, with two variables, we come up with one variable alpha. See, summation of alpha I minus here half minus 1. These two terms are similar. Notice that these two terms are similar. And this will be half times of this. On solving the first condition, we came up with three results. This A, W of alpha, this summation of alpha y equal to 0, and this w. Now let's apply the second condition. What is second condition? Multiplying the Lagrange multiplier with the constant equal to 0. Our constant is this, Lagrange multiplier is alpha I. If we know that one should be 0, not both of them. And if the constant is 0, what does it mean? What does it mean? And we also know that the Lagrange multiplier should be greater than or equal to 0 from the fourth condition. What does it mean? Let us suppose this constant is 0, right? Means yi of wi dot xi plus d equal to 1. This is now, if yi is plus 1, what is the equation? W dot xi plus d equal to 1, right? W dot xi plus d equal to 1. This is the equation of the pipeless. This is the equation of the pipeless hyperplane. Let me show you that. Let me show you that, guys. Let me show you. See, this is the equation of the pipeless. You can see, right? This is the equation of the pi plus c. W dot xi plus d greater than or equal to 1. What does it mean? If xi's are lies on this line, if xi's lies on this line, those will satisfy the equation, and this greater than symbol will become to equal to 1. It means though the vectors, the support vectors will be having the Lagrange multiplier value positive, greater than or equal to 0. We understood that the support vectors will have the Lagrange multiplier greater than or equal to 0 with this condition 2. Now let's apply the condition 3. I applied it, no use I think. Now to compute W, now see guys, we want W and D. To compute W, we need alpha is, right? Because W is equal to this. We want alpha I. And now to find out the alpha I, we have to find out the alpha 1 to alpha m. Alpha I is nothing but m alphas we have. Before, when we have two Lagrange multipliers, we solve four cases, right? We solved four cases if we have two Lagrange multipliers. See, case 3 up to 4 cases. Imagine, guys, we have m Lagrange multipliers. It will be a very tedious task for us to do manually, right? You agree with me or not? It will be very tedious task. Now, what is the solution? The solution is to create an algorithm. To create an algorithm which will do this task. Now, how to create an algorithm? The algorithm is there, the package is there, but how to apply? Now the wolf comes, the another scientist comes to KKT and says, "Hey Wolf and Lagrange, convert your Lagrange, your optimization function to my optimization. You reformulate your problem to my problem and use the algorithm. Use the algorithm." He says, I hope you understood the conversation. Why the pain? Why we need Wolf? Why we need KKT? Why we need the Lagrangian? I hope you understood. Think about it. We should apply the algorithm. Now, how we want algorithm to apply an algorithm? We want to convert. We want to reformulate because the algorithm is developed in some other format, some other formulation. We have to change. To change, Wolf will help us. Wolf dual problem. We will explore this in the next video, part 3, which is very important. I will show you the code as well, the package code. I'm very excited. I hope you understood something. I hope you understand. If you have any doubts, please drop in the comment section, guys. I'm very happy to answer your doubts. And let's get to the next video. I'm very excited for that. And if you got any value, please like, share, and subscribe. Thank you for watching the video.